All right, so let's continue with the last lecture, basically, of our semester. A few quick things. I will have the sample final exam posted on Canvas. Free to check it out so that you can prepare and ask me any questions about it. During the break, we'll discuss the format of the final exam as well, because I want to give you guys more time to work on it, just because we have time. Why not, right? I want to make it a little bit more open-end so they can take a deep look into different problems, and I want to use the exam to kind of like further leads you to read more things or learn more things, right? So that might take a little bit more time, but I think at the end of the day, you gain more experience. And fun fact, when it's more open like that, you should treat it as many of these are free points, because it's just your opinion. If you have a scientific way to back up your opinion, you should be fine, right? Just don't randomly throw things into ChatGPT, because they will be wrong. These are advanced class. I'm pretty sure there's no way they can answer that. Today, we will wrap everything up with a concept called network on chip. And to be fair, about interconnects and how to connect things together, because this is one of the used to be emerging topic, because we have a single chip. We want to connect a bunch of cores together. Now, it becomes another emerging topic as well. You have multi-chip module, basically, as it's really hard to build a big chip, right? Making a big chip is really hard. People are thinking into like, okay, let's break the big chip into smaller chiplets. Each one of them is smaller, but you can then connect them through another layer called the interposer. Basically, it connects the smaller chip together, making a big chip again, right? So if you think about that model, things becomes the network, right? And here is what we're gonna talk about. So first, the fact that you have a bunch of cores, right? A bunch of cores, 4 core, 8 core, 16 core. You need to connect them together. Somehow they have to be like put together, right? So quick recap. What's the assumption that we make when we access the cache, right? Sending an access is free. Like you go to the cache, you spend time looking up, you spend time accessing the data, but sending the actual request, hey, I want to access the cache, that is free. That's what we assume. We have unlimited bus bandwidth to support that somehow, right? Is this true? In a small system, yes, you have a bus. It connects like one CPU to a cache, right? Now, let's imagine you have 30 cores or more, which, well, I mean, nowadays it could be something you look forward to in the 5 or 10 years, right? Even now, I mean, if you buy data center chip, it will have multiple core up to 20 or 60, right? In one package. So the problem is, in that case, right, to access the on-chip cache, if I use a bus, it means one person can use it at the time. One person can use it, right? And the data request need to go to the correct location, because the cache can be anywhere on your chip. Because only one person can use it, it means that if I have, say, 16 core 1 want to access the data, it goes to the cache. In the meantime, core 2 and 3 and 4 suddenly say, hey, I want to access my cache too. No one can use it because core 1 is using the bus. They have to queue it up. Imagine you only have one golf cart that can only transport one person, and you're in a small complex that need to go around with the golf cart. With this, if you want to go anywhere, you need to wait for the golf cart, because that's a bus. You will then realize that this is not efficient. You need something better, right? Again, let me translate this entire, right? Just so you can think about it and generate some internal question. ก็คือเวลาเรามีคอหลายๆคอเวลาที่มันจะเชื่อมไปที่แคชนะครับมันสมัยก่อนเราจะใช้สิ่งที่เรียกว่าบัสเนี่ยก็คือสายไฟเส้นหนึ่งตุ้มยาวๆใหญ่ๆแล้วเวลาเราจะไปที่แคชปั๊บก็จะบอกเอ้ยเราขอ data request แล้วก็จะวิ่งไปที่บัสแล้วก็ใช้มันถ้าผมใช้บัสตัวนี้อยู่สมมุติผมเป็น CPU 0ผมใช้บัสอยู่ CPU 1ถ้าต้องการไปที่แคชมันต้องรอผมมันจะต้องรอจนผมใช้บัสเสร็จแล้วมันก็จะใช้บัสได้ให้นึกเหมือนสมมุติว่าเราอยู่ใน complex เล็กๆแล้วมีสิ่งก่อสร้างหลายๆอันแล้วมีรถกอล์ฟ1 คันแล้วการที่ผมจะไปจากที่หนึ่งไปอีกที่หนึ่งเนี่ยผมต้องใช้รถกอล์ฟเพราะว่ามันใหญ่เกินกว่าที่จะเดินแต่ว่าไอ้รถกอล์ฟเนี่ยมันนั่งได้คนเดียวแล้วมันมีคันเดียวอันเนี้ยคือบัสแล้วจำนวนคอก็คือจำนวนสิ่งก่อสร้างที่มีเพราะฉะนั้นสิ่งก่อสร้างแต่ละจุดเนี่ยผมอาจจะวิ่งไปไหนก็ได้คือผมก็คือ CPU แล้วผมจะต้องวิ่งไปแต่ละที่เพราะผมต้องส่ง data request ไปเราก็จะเห็นได้ว่าโมเดลเนี้ยมันมีความจำกัดมากๆในเรื่องว่าแล้วเราจะทำยังไงให้มันแบบ scale ได้เพราะว่าผมต้องส่ง data request ไปมารอบๆตัวนะครับ so that is the problem with the bus interconnect right but you need the cache and you need to scale you need more core so the key idea is you somehow need to magically find a way to link things together right and the share cache will span across multiple locations on the ship as well because your ship is a 2D surface. You need to somehow connect them and place the cache around, right? Sometimes it's not next to you. Sometimes it has to go around and go to another core memory. Laying things out is a topic that is quite important nowadays. Actually, you go to listen to circuit people. They're like, how do we build this thing and put it on the chip because it's so hard and so compact, so small, right? And to access the piece of the cache, it would take a different time. Imagine I have to go to the further building. It would take me more time. So you have a new concept called NUCA, non-uniform cache access. So my cache access can take some time. Non-deterministic. It can be sudden, like 2 cycles, 3 cycles, 4 cycles, or longer time, right? It can be longer. Traditional, as I said, imagine a bus that connect one place to another. And if I have to use the bus, I have to wait at the bus stop and there's only one car, can only fit one person. That is a bus. In the CPU, it connects 2 locations together or more, basically connect multiple locations together. But you have to queue up to use the bus, right? So that's the downside. The benefit is it's really cheap to implement a simple bus. The downside is it takes time if the bus is long, right? It's not super scalable. If I have more things, more people to use the bus, it will be stuck because I cannot really use the bus. So in the medical era, modern CPU have more cores. I mean, if you look at the recent chip, you're looking at something like 16 core, 32 core easily, right? The bus are not going to scale, right? What if there's 2 cores that want to access cache at the same time? They have to queue it up. Now, what we can do is to bring in the concept that we learned so far a long time ago. How do we connect multiple computers together? Because CPU is a computer. So can we apply the same concept? Can we apply and build a network, but it's on the chip, right? So basically what we want to do is to build a network that connects a bunch of things together, right? So I can start to use different network topology to fix this scalability issue. And one of the simplest, right? One of the simplest topology I have is a ring topology. So let's think about it, right? So let's use a ring. It looks something like this. The blue box is the CPU core, right? In this case, I built a bus connecting each adjacent core. I have the east and the west neighbor, and that's it, right? So the vertex is a node, which has a router. The router can send the packet in and out. And a node can be a CPU with the cache. It can be the memory controller. It's a location you want to go to, and you can send things around, right? So let me translate this in Thai just to make sure everyone understands it's on the same page. ก็คือถ้าผมสมมติมี4 คอหรือ 8 คออย่างเงี้ยระบบเน็ตเวิร์กที่ง่ายที่สุดใน on chip network ที่ผมจะทำได้ก็คือเป็นริงก็คือผมเชื่อมตัวข้างๆจบผมมี8 คอเป็นวงแหวนที่มี8 โนดอยู่ในนั้นแล้วแต่ละโนดจะมีเราเตอร์อยู่เราเตอร์เนี่ยมันจะส่งแพ็กเกจจากโนดนั้นไปที่โนดอื่นๆได้แล้วในโนดอาจจะมีอะไรบ้างจะมี CPU จะมี CPU กับ cache จะมี memory controller คือเราสามารถแพ็กเกจพวกนี้เข้าไปในโนดได้นะครับ so that's the topology. Then I just talk about this thing called a packet. Packet is basically a bulk of data, right? is being used to send things around. When I want to request a cache, for example, I generate a data request packet, right? But the thing is, the data packet is big. It doesn't always fit in the link. Imagine there's a small link in the CPU, right? If you make a big link, it will consume too much energy. So what we do these days is basically we break the packet down into something called FIT. Basically, think of packet as a worm, and you slice the worm into smaller chunks. For example, a 64-byte cache line can be broken down into 8 chunks of 8 bytes data flit. Then I add the header flit to say, hey, this is the information. This is where I'm from. It's where I want to go, and here's my address. And then I route the flit through the network. How, right? Basically, when you have the router in the network, they would have the input and the output port. In this case, for example, right, you have the, if you look at this, like let's say you look at this middle node, right? What you have is basically the west output, the east output, right? You also have the east input and the west input. So this becomes the port. Each port will have the buffer to put things in. Basically, you send a bunch of data over, you put them in the buffer, the router consumes that forward to the location, right? When I said forward, you can go to the east or the west output, or you can also inject and eject. So you can go up and down here. Going down, we call ejection. This is injection. Injection, basically you put another item into the network. Eject means you take it, send it to the CPU, send it to the cache. All right. So in this case, if you have the basic ring topology, you have 2 ports, east and west, and then you have the injection, ejection. So by default, every node would have the injection, ejection port. So that's the ring topology. If you want to make it even more scalable, because one of the downsides of the ring topology is cheap, it's simple, it's really elegant. If your node is only for 8 nodes, let's imagine 16 core is not going to really do well in a ring because you have to go through multiple hops to get to your destination, right? So to address scalability, many people have been using this 2D mesh. The way it works is something like this. I have 16 nodes. I'll do a 4 by 4. I have each node can have up to 4 ports, right? North, east, south, and then west, right? North, east, south, west. That's it. And with the network, you need to then figure out how to route the packet around, right? So the policy can basically impact your performance, right? Because each hop will take a number of cycles, and the packet can require the same output port, right? So how do we handle this? For example, I can have a packet from here, source, want to go here, and another packet, so source 1, destination 1, source 2 here, destination 2, basically going to the same node here. This node maybe can go here. This node maybe can go here, right? But you see that they share the same path here. So it basically means that then I need some strategy or who get to use that link, right? This basically would lead us to the next problem called routing. How do we plan the path, right? So one quick idea is we can do something we call XY or YX routing. XY routing, basically I go to the X direction first, then I go Y direction. For example, XY routing for source to destination here would first go to the X, then go to the Y. Another source, go to the X, go to the Y. Another source here, destination here, I go to the X, then I go to the Y. Simple, right? And it's deadlock free. It's a deadlock free design because you will always drain your packet. If there's enough buffering, XY routing will always drain the packet. It means that you will make forward progress. the downside of this, you see already, because things share the path, you can have congestion. Some link will get used more often than other. Some link is going to get used more often than others. All right. Any questions so far? มีคำถามไหมครับ อันนี้ก็คือ xy routing ก็คือบอกว่าเราจะไปแกน x ตามด้วยแกน y yx routing ก็เหมือนกันเราไปแกน y ก่อนแล้วตามด้วยแกน x ข้อดีคือมัน simple แล้วมัน deadlock free ก็คือ deadlock free เราสามารถ prove ได้ว่าไอ้ destination ของทุกๆ packet อ่ะมันจะสามารถ absorb packet พวกนี้ไปได้คือทุก cycle มันจะมี forward progress แล้วมันจะไม่มีเคสที่แบบมันล็อกกันเองนะครับแต่ว่ามันจะมี congestion ก็คือเหมือนเวลามีถนนที่แบบอย่างสะพานตากสินตรงสาทรเนี้ยมันเป็น bottleneck อ่ะคือทุกคนต้องวิ่งผ่านสะพานนั้นอ่ะก็จะเป็น congestion อันนี้ให้ทุกคนนึกภาพเหมือนถนนเลย ก็คือบางถนนบางเส้นคนใช้เยอะก็จะรถติดพอรถติดปั๊บเกิดอะไรขึ้นเวลาที่เราจะไปถึง destination ก็นานขึ้นนะครับผมจะชอบเทียบ network on chip กับการวางผังเมืองแล้วก็วางถนนที่แบบเชื่อมแต่ละจุดเพราะมันก็คือคอนเซ็ปต์เดียวกันแพ็กเกจก็คือรถของเราบางรถบางคันใหญ่รถบางคันเล็กถ้ารถใหญ่ก็จะใช้บัฟเฟอร์เยอะหน่อยแล้วเราก็ต้องวิ่งจากที่หนึ่งไปอีกที่หนึ่งนะครับ All right, so since there's no question, let's talk a little bit about deadlock, right? This is a really important concept in network on chip because it has to be first of all deadlock free, right? For example, if I'm trying to get from here, oops, sorry. Let's say I want to try to get from pointer here. Want to get from here, then take a turn here, right? But to take a turn, this means that I need to be able to get to the buffer, right? And then why not keep moving? Sorry, so I have a really fat hand and it touched the both the tablet, so it actually thought I was clicking. Then I have another packet that need to use this link, right? Need to use this link. It occupy the link. It occupies the link. But then I need to make some kind of turn. But another packet basically say, hey, I want this link as well. Want this link. But I cannot use the link because I'm occupying this link. So basically packet P2 occupy this, P2 occupy this, P1 occupy this. But P1 want to use P2's link. P2 also want to use P1's link. In that case, I'm stuck, right? Now, if you look at XY routing, why are they deadlock free? Because packets flow in the same direction. The reason why these are locking each other is not because the link is occupied. It's the buffering that take things out of the link are occupied. I cannot allocate any more buffer for that particular link, for example. My packet would be stuck. I cannot go forward. To go forward, I need to free up the buffer, but to free up the buffer, that buffer is also tied by a different packet that uses another link. So I have this cyclic dependency. If you look at XY routing, you are not going to have cycles. So you always go from one axis like X first, then Y, right? So you will share the link, but it's guaranteed that if you take the link, you can get to the destination because no one else is going to take any turn and occupy that particular output, right? So before we continue, there's more things to look at because I just talked about deadlock and then I said, hey, there has to be a buffer in the router, right? So let's look at these in detail. What do we need to actually route the packet? We already talked about input and output port. You need some input, we need some output. We need some logic to figure out, okay, given this packet, it wants to go there. Do I send it toward this output or this, do I send them north, do I send them east, do I send them west, or do I send them in the south direction, right? Then you need some logic to say, if I'm at the destination, do I eject to the destination? If I have new things coming in, how do I inject into the network? Then you need a buffering to store the flit in the packet, right? So first of all, let's go through one of this thing in detail. The first thing is arbitration logic. Let's use ring as an example because it's simplest, all right? So you have the core, which injecting into the network, and you have the east and the west direction, right? So how it works is I'll have a packet here. It then figure out, okay, where do I need to go? The arbitration logic will figure out, okay, if I have to go east, do I have the buffer for this? If I have the buffer, I send this over to this location here. And basically it goes this way. If I have the incoming packet east, for example, this guy, right? I say, hey, do I have the buffer here? Yes, I will put the buffer. I will basically allocate the buffer, send the packet over, forward the flit. So these are flit. Flit is a part of a packet, essentially, right? In a 2D mesh, there can be some more conflicts. For example, I have the west input that need to use the east output. The north input also need to use the east output. Both of them want to use the east output. You have two incoming packets, right? So you have the router here. You have incoming packet from the north and another one from the east. Both of them want to use the east output. How do we do this? So the arbitrator will determine who get to use the east output. The other flit wait. That's all. It's like when you have a traffic crossing, right? I want to go there. Another car on the other direction want to go there. You then figure out who takes the turn. That's it. Then you have this topic. To actually improve on the design, you can do something called wormhole routing. The way wormhole routing works is treat packet as if they're going through the wormhole, one flit at a time. And you don't actually have to route the entire packet in one go. I don't need to route the entire packet in one go. I just need to make sure that the remainder of my packet goes to pass through the router. Then you just need to make sure you still have the whole packet at the end. Don't kill the worm by slicing packet in the middle and reshuffle them, right? So let me translate this entire a little bit. So the idea is ก็คือผมมี packet ก้อนใหญ่ๆอยู่ ผมต้องการส่งไปที่เป้าหมายฮะ คือถ้าผมจะส่งทั้งก้อนใหญ่ๆเนี่ยมันเปลือง resource ผมสไลด์เป็นฟิตเล็กๆอยู่แล้วทีละ8 ไบต์สมมตินะแล้วผมส่งผ่านลิงก์เนี่ยผมจะสามารถส่งผ่านลิงก์ไปได้แล้วก็บอกว่าเอ้ยตอนแรกผมขอส่ง4 ฟิตก่อนส่งไปแค่4 ฟิตแต่ถ้ามีคนจะใช้เอาพุทอันนั้นอ่ะก็ให้คนอื่นใช้ก็ได้คนอื่นก็จะส่งไป4 ฟิตเหมือนกันก็ตามใจเขาแล้วผมค่อยส่งฟิตที่5 6 7ก็ได้ก็คือเราไม่ต้องส่งทั้งก้อนในคราวเดียวกันเราส่งทีละครึ่งเราส่งทีละ2 ตัวเราส่งทีละตัวก็ได้เหมือนกันอันนี้เขาเรียกว่า wormhole routing นะครับ So let's go through some example here. So let's say I have the router in the middle. So let me draw it a little bit big here, right? I have the buffer at the output port. Let's say everyone wants to use the output port here, right? And I have an incoming flit in the buffer here and here, right? Both want to use the same output. One thing I can do is I can first send this guy here, then this guy here, right? Now, let's say I have another person, I mean, obviously in this case, there's another box here that want to send to the same direction, right? I can then forward this to here as well, occupying this blocks, and it can keep sending the blue flits, right? My point is, I can keep doing this. I just need to make sure I can tell which are the red and which are the blue, okay? ก็คือผมสามารถทำอย่างนี้ได้แล้วผมแค่ต้องการการันตีว่าเราเตอร์ผมมันจะบอกได้ว่าไอ้ตัวไหนสีแดงตัวไหนสีน้ำเงินเพราะเราจะได้แยกออกว่าอันนี้ฟิตของใครนะครับอันนี้ฟิตของใครแล้วเราจะได้ make sure ว่ามันสามารถ make forward progress ก็คือมันจะไม่สตั๊กอยู่ตรงเนี้ย แต่อยู่ครึ่งตัวแล้วก็ต่อไปไม่ได้ so how to make the guarantee that they can proceed forward you can use a concept called virtual channel the way it works is the output have buffering right it's a big buffer one thing I can do is to dedicate this into virtually this one big buffer or multiple channel so let's say this is a big buffer right I would say this is channel 1 this can be channel 2 and the remainder can be channel 3 if I'm using channel 1 for the blue slit if I'm using channel 1 for the blue slit they will take channel 1 basically the blue slit anyone from the blue packet will use channel 1 this way I can say okay anything coming from channel 1 I know it's from one packet if I'm from the red packet I'll use the different channel so in this case the red can use the second channel and if I have another packet wanting to use the same output right I want to use the same output I can then say hey I have that orange packet that want to use the third channel this way they can also use the third channel and the target will look at the front of the channel take slit in I just need to make sure that whenever I have a new packet the new color whenever I have the new color I will allocate a new channel for them. So it's one color per channel. My buffer can have multiple channels and they would occupy the channel to make sure that that particular packet use just that channel. And this applies to all the router. I can then forward to the next location by saying, hey, is there any free channel? I'm a new guy. Oh, okay, that's free channel. I go in, I use the channel, I keep forwarding. So each channel is used for one packet. Each channel is basically then used for one packet, right? So you want to put everything together. Let's say you have a 2D mesh, right? Each one of these will have buffering. Oops. Again, I need a pen. All right, I need to use buffering. I have buffering, right? Basically, it's a buffer. I will use the different channel using different color. Okay. I have the orange channel, the red channel also in buffer. I have the blue channel, right? And on the input port, output port will have this channel. So then you have the arbitration logic that can basically forward incoming packets into one of these channels. Use and occupy different channel. That way, whenever the link is free, it picks one of these, forward them into the next router, and do the same thing for the next router. It forward to the next destination. It then forward to the next destination and then forward to the eventually wherever they want to go. Now you have a functioning network on the ship. So this way you have a functioning network on the ship. All right. So what are the design issues, right? Now we have a functionality. I'm not talking about too much about performance, right? What are the different things that people work on to improve performance? So let's take a quick break. After we come back, we will then move on to what are the things that affects performance. If you're in network area already, you might have known some things about this, right? But let's go over them together. So again, we'll do a quick break. We will resume. Now that we have the fundamentals on network on chip, we will then resume about what are the potential bottlenecks that can block us basically from making fast progress and have a really high performance chip. All right.